Hello, everybody, again. You are welcome to clip 5 of part 2 digital communication in the course of modern wireless communication and applications. In clip 4, we arrived to this slide about error control coding. And as we mentioned, error control coding refers to the process of adding some redundant bits to the block of data of information, and the target is to make it possible to detect if error happen, or and in some cases also to correct the error at the receiver side. So the idea here that it will be able to manage with the environment such as noise, interference, and fading of the channel. So as it is mentioned here, the channel coding can provide as much as 10 dB of performance improvement at low cost. Actually, this is very big like improvement that it can be achieved by channel coding. What we mean by 10 dB performance improvement, for example, assume that you use transmitter, digital transmitter, and digital receiver, and let's say that you use 1 watt of the transmission. In some cases, you can reduce this power to by 10. It is like 0.1 watt you use for transmission, and you will get the same performance almost, but with using this channel coding, proper channel coding in some cases. So this is called the coding gain. So you can get much high improvement without actually increasing the transmission power, or sometimes with transmission bandwidth, because with this coding we can increase the spectrum efficiency without sacrificing the probability of error. Because as you mentioned, or if you remember from previous clip, we said that when we increase the channel or the spectrum efficiency, what we lose? We lose the performance, because the probability of error will be increased in that case. However, with using coding, this could give us the chance that we can increase the spectrum efficiency without like sacrificing the performance of the system. So channel or error control coding is essential and is very important in any digital communication system. Okay, the coding is achieved by, as I said, by increasing some bits, which is not part of the information itself. Of course, it is related to the information, but it doesn't carry information about the source. I mean that we want to send. So it supports the transmission. The code rate, we call the code rate. The code rate is the number of information bits divided by the total number of bits. In case that we don't add any coding bits or redundant bits, of course the code rate will be 1. But if we have information bits like per block, assume that we have information bits of 5 bits, but we added 5 redundant bits for the coding, then the total number of bits per packet will be 10 bits. And then in that case, the coding rate will be 5 divided by 10, and this will be half. So as the coding rate becomes closer to 0, or it is much less than 1, as it means that more bits or redundant bits have been or has been added to the packet. As we are closer to 1, then it means that high coding rate, which means that most of the bits are used for the information data. As we increase the number of redundant bits, it increases the capability of the coding in general. So capabilities means that how many bits that we can detect in error, and also the capability of how many bits it can be corrected when one or more bits received in error in a bare packet. However, increasing this capability of correcting errors will reduce the throughput, because we take some of the bits used to be information to use it for redundant bits. So we need always to compromise. But remember that using error control coding, it gives us the opportunity that we can also that we can use higher spectrum efficiency, and this could complete the picture. What kinds of error control coding we have? So we have error detection and retransmission. So in the receiver side, we don't implement the correction of the errors, but only detection of the error. So if the packet received in error, then it will be detected. Of course, we will see how and how it works. This will be seen later, but now we just talk about the new kinds of error control coding, that only we detect the error. Once it is detected, we don't try to fix it or to correct it, but we ask the transmitter to retransmit the packet again. So every time the transmitter sends the packet, they should receive also acknowledgement that the packet was received correctly. So in the receiver side, we only detect if there is error or not. Of course, what is the benefit of using error detection and retransmission? It is also named as automatic repeat request, ARQ. The benefit of using ARQ, that simplify the receiver side. So the receiver side, because implementing the error correction, it can sometimes complicate a little bit the receiver side. Of course, this was like maybe true maybe 40 years ago, something like that. Nowadays everything is done with like based on microcontrollers, so it is not that big the difference actually about the complexity of the receiver. However, there is one serious problem of that using fraud error correction. If we want to increase the capability of to detect and correct the errors, usually we need to use more bits for as a redundant bits, so the coding rate can be small. And coding rate, when the coding rate is small, then we sacrifice some of the information bits, which means that we reduce the throughput. So this is one major like benefit of using automatic repeat request, that we use very small number of redundant bits, and we just to detect if there is error in the packet, so we don't try to correct that error. The second kind is called forward error correction. Forward error correction is the scheme where the detecting of the error at the receiver and also correcting the error. Also correcting the error. Of course, it has some benefit of using forward error corrections, that we don't need to make like retransmission. Retransmission process actually, this is one of the disadvantages of ARQ, that it will increase the latency, the delay, because once the transmitter sent the packet and the packet was not received correctly, then the receiver will ask the transmitter to retransmit the packet again, and then every time retransmitting the packets, it can introduce big latency and delay in the network. Also, it increases also, of course, the competition, especially in contention based like networks. It will increase the competition for the retransmission, and it will delay many packets, not only for that pair but also for the other users in the channel. Also, ARQ sometimes is not possible to be used when the receiver doesn't have like capability to transmit. So because in ARQ we need always two ways transmission, so that means that the receiver should be able also to send back to the transmitter that to retransmit. Okay, so this is a two-way or duplex transmission. This is needed in ARQ, and sometimes that we have like a receiver that cannot communicate with the transmitter. The receiver cannot communicate with the transmitter. In that case, of course, it is not possible to implement the ARQ. Another problem of ARQ, that it will be solved here with FEC, with forward error correction, that when the delay is very large. For example, if you use communication over satellite, so we know that the satellite communication, especially for stationary satellites, it can be like very large delay, can introduce high delay for every packet. So retransmission will introduce very high delays in that sense. Okay, so forward error correction is very nice algorithms, that it will support the way that we can detect and also correct the errors at the receiver without the need to retransmission. Of course, we have hybrid system, as we will see them. They are widely used, especially in 5G and 4G. Hybrid ARQ. It is ARQ system, but also it uses some FEC, like low capability forward error correction when we have a small error, or at least we can distribute them over more than one packet. So when you receive a packet in error, and then you can ask for retransmission, and with the when they retransmit it again, so using forward error correction distributed over more than one packet, it can be used for error detection and correction at the receiver. So we can use hybrid ARQ system. So let us start with ARQ. So we can see here that automatic repeat request with stop and wait. This is the simplest one. So in the simplest one, that the transmitter, you can send packet 1 to the receiver. So the receiver receives packet 1, but it will not send again. So the transmitter stop waiting until it receives the acknowledgement. So the receiver will check the packet, and once the packet is okay, so they send acknowledgement, and the acknowledgement is received by the transmitter. Once it is received as acknowledgement, like positive acknowledgement, then the transmitter will send the second packet. And once the second packet, of course, there is a delay between the transmitter and the receiver, and then after some processing, they send acknowledgement, and then they send the third packet. But it is clear that the third packet was not received correctly, so they sent negative acknowledgement, which means that it was not received, or without receiving any acknowledgement, means that the packet was lost, and in that case the transmitter will send the same packet again and it will repeat sending them again until it receives acknowledgement. Of course, there are some algorithms that it can be resent for certain time. It can be fixed in the protocol that how many times they should resend the same packet. The second kind of ARQ is called continuous ARQ with pullback. In that case, we have like full duplex channel, so the transmitter will not wait until it receives the acknowledgement. So they continuously sending the packets, as you can see, packet 1, packet 2, packet 3, and in the same time the receiver sends back the acknowledgement. So every packet was decoded correctly. They sent acknowledgement, and once it received some packet with error, so it was not decoded, then they will send like negative acknowledgement. Once it is sent negative acknowledgement, then the transmitter will resend again the errors packet, the packet which was not received correctly, but also they will send all packets after that. So once the receiver receives packet in error, so they will just wait for until it receives it again, and then they repeat. The transmitter will repeat all packets again. It has, of course, some benefits here, because sometimes in fading, when you are in fading, and the fading takes longer time, so it means that if one packet was not received correctly, most likely even the second and third packets will not receive it correctly as well. The other kind is called continuous ARQ with selective repeat. So in this case, and this is the fastest one, so we we resend only the packet which was not received correctly. So you can see that here they send packet 1, packet 2, and it is the same as the previous one, so that every time they don't wait, they decode and they set acknowledgement, and once it receives the packet number 4 in error, so you can see that once it is received to the transmitter, that packet number 4 was received in error, so they retransmit packet number 4 alone. So they don't send everything, so they send only the packet which was received in error. This is called continuous ARQ with selective repeat. And as I mentioned, this is the hybrid ARQ. In the hybrid ARQ, that it has like more advanced technology than the ARQ, so they use also part of that forward error correction, but in the same time they use high rate. So using high rate means that we don't sacrifice the throughput. In the same time, we have the ability to request the retransmission, but every time we request the retransmission, it is possible that to distribute this FEC packets between them, so we increase the capability of the receiver to decode the correct code from two consequent retransmission of the same packet. Okay. So as we said that the major advantage of ARQ over forward error correction is the error detection requires much simpler decoding requirement and much less redundancy than does error correction. Sorry. Okay, now we talk about forward error correction. In the forward error correction is preferred, as we mentioned, in some cases that when the reverse channel is not available, or sometimes it takes very long time, that retransmission strategy is not convenient implemented when the expected number of errors is high. It's sometimes that where the channel is very bad, so we expect always errors. So the probability of packet error, let's say 20%. So in that case, 20%, what it means that 20% of the time will be used for retransmission, and every time you retransmit, so every retransmission it has also 20% probability that it will be retransmitted again, and so on. So this would be a problem. So we need always, in that case, to go to the forward error correction, which gives much like stronger algorithm to handle such situations. Okay, so in forward error correction, the bit error rate, depends on the received, as we said, EP over N0, and the modulation method. So one may reduce the bit error rate by increasing EP over N0. So when you increase the signal to noise ratio, the bit error rate or the probability of error will be reduced, as we mentioned before. So as we mentioned also that EB over N0 or the SNR could be increased by increasing the transmission power. However, increasing the transmission power is not always good option. Why? Because first, for every algorithm or for every standard, we have like maximum power that you can use. It is not, for example, for Bluetooth, you cannot say that I want to implement a Bluetooth with transmission power of 10 watt. It is not allowed by the standard. Okay, so every standard it has some maximum power. This is the first problem. The second thing, increasing the power will not solve the problem. If you are in multi, like there is multiple access or there is different users use the same channel. Increasing the power means that you increase the interference to others. Increasing the interference to others, what will happen for them? For them, their EB over N0 or their signal to noise ratio will be reduced. Reduced by what? Not by the noise, but because your interference, because you increase your power. Okay, so what happened for them? They will lose the performance in their system. How to solve their problem? Everyone will increase their power. So in that case, we'll have the very high power, very high interference, and most likely the communications, most of communication links will be failed. So the only one that ones that they will get good access, those which have very good channel, for example, they are closer to their receivers. Otherwise, the channels will be blocked. So increasing the power is not a solution for that. So the best solution in this case is one of the best solutions is using the forward error corrections. For using forward error corrections, that even with a small power we can handle the errors by correcting the error. So this is called the coding gain. So the coding gain is computed as in this way. So it is EP over N0 for uncoded to achieve certain probability of error. So for example, at probability of error of 10 of the power minus 4, it means that every 10,000 bits, there is a chance that we will have 1 bit in error. Okay, so for example, to achieve this, we would need EB over N0 for uncoded that one. Okay, in dB. For example, it was, let's say that we need 15 dB for EB over N0. And now with coded, with the capability of correcting the error, maybe we will need, for example, only 10 dB. Okay, because if there is one error happen, then it will be corrected. Okay, so in this case, 15 minus 10, then we will have coding gain equal to 5 dB. The coding gain can be up to 10 dB in some cases. So you can see this is, for example, for the uncoded, and this is for the coded case. So for the coded case, for example, with EP over N0 equal to 4 dB, so you can see this is the error. But if it is uncoded, then the error would be much higher. Okay, now we come to a very important question. How it works, how it is possible that we detect error, or how it is possible to correct the error. So both of them, this is very important question to be asked, and we will try. Of course, there are too many algorithms that are used for error control coding, but we will talk about the conceptual idea, how those algorithms work, or what basis those algorithms are based on. Okay, the idea here that we use redundant bits. What is the meaning of redundant bit? Okay, let us introduce in some simple way. Assume that you have 3 bits of information. All of them, they are information. So every time that you have series of bits based on, for example, from your source of data, you have microphone. After that, you have like analog to digital converter. Analog to digital converter gives you like stream of bits representing this data. Okay, so assume that you take 3 bits by 3 bits. So all these 3 bits are packet. So every 3 bits are the one packet, for example. So this packet actually of 3 bits representing every bit is information bit. So every bit is important in this case. Okay, now um, per packet, because every packet has 3 bits, so how many possible like combination out of these 3 bits? Okay, 3 bits means that 000, 001, 010 until 111. So we have 8 possible combinations. Every combination can be one kind of data of the information. For example, 000 can be the information 000. The information can be 001. The information can be 010. So every one of those 8 can be the information. Okay. Now let us we added 2 extra bits to these 3. Okay. So how many the number of bits now we have per packet? We have 5. Okay, this is called, by the way, this is called block coding. This is called block coding. So we have 5 bits per packet. 3 out of those 5 are information bits. The other extra 2 are the redundant bits, or sometimes called parity bits, or they are also called check bits. Okay, but now out of those 5, how many combination we have? We have 32. Okay, so now we have 32 possible combinations of those 5. How many combinations are allowed? Only 8. 8 out of 32 are valid, because those which determine the valid packet are those which can be one of those 3 bits. Okay, the other 32 minus 8, all the others combinations are not valid. Okay, now if we design the code in the way that we design the code, we have 3 bits of information. They are coming to the coding. The output is 5 bits, but we design the code in order to keep the valid bits as far away from each other. So this is valid bit. Okay, this is valid packet. Sorry, this is a valid packet. So if one error happen within this valid packet, it will never become another valid packet. If one error in any of those 5 happen, though there shouldn't be another valid packet, so it should go to invalid packet. Okay, so in that way we can keep the distance from the valid packets as far away as possible from each other. Okay, now if one bit received an error out of those 5, then we know that it becomes invalid packet, so the receiver knows the valid packet. So we have those 8 valid packets, we know them. So but the received one was not one of those 8, then we know that this packet, it has like one or more errors. So we know that there is error because it is not one of the valid packets that we have. Okay, then one may ask, what if 2 or 3 errors happen? Yeah, in that case, if for example 3 errors happen and it becomes another valid packet. Okay, in this case, it is called undetectable error pattern. Undetectable error pattern means that many errors happens within the same packet, which causes the resultant packet to be another valid packet. So the receiver will think, okay, this is valid packet, I have it, but actually it was errors because many errors happened within the same packet. Okay. Now the question, what is the benefit in that sense? Okay, now if let us assume that every bit in those 5 bits, so now we have 5 bits, as we can see that we have 5 bits. Okay, let us like this is bit 1, bit 2, bit 3, bit 4, bit 5. 3 out of those are valid, as we said. 2 out of them are invalid, redundant bits, and 3 of them information bits. Okay, now if we assume that every bit will see independent channel, okay, and the probability that you will have one error in this 5 bits is p, and let us b is 10 of the power minus 3. Okay, what is the probability that you will the packet in this packet that you will receive 2 errors in that case? Okay, in this, the probability that you will receive 2 errors in this case is related to the b square. Related to b square, we can make the calculations based on like uh, based on binomial distribution. We can calculate exactly what is the probability of error in case that we have 2 out of 5 in error. But let us leave this now. So the probability that you will have 2 errors will be related to b square. Okay. So related to b square. So example, if it is this one, the probability of single error is related to 10 of the power minus 3. The probability of 2 errors is related to b squared, means that 10 of the power minus 6. So if the probability of one error is, let's say, is equal to 10 of the power minus 3, it means that every 1000 packet we will have one packet with one error. For example, of course it will be 5 times this, but let us ignore this now. And the probability to have 2 errors in one packet of 5 bits, it can be about couple of million bits, the packets that we will have 2 errors in the same packet. So now you can see that the probability of having more than one bit in error in per packet is much less than the probability of having only one bit error. So having 2 bits is much less than the probability of having 1 bit. Having 3 bits is much less than the probability that you having to have 1 bit or 2 bits, and so on. Based on this fact, then the using the coding or the block code, it will give a lot of benefits. So if we are able to detect even one error or one packet error and correct it, it will introduce a lot or high performance in the digital communication system. Okay, so this is the main, of course we are going now to discuss this in more details. We will see now like more examples about what I am saying now, but this is the general concept of the block code. We have another convolutional code and we have different kind of codes, but all of them, they are based on the same concept: keep distance between valid codes. Okay, keep distance between valid codes. As you have far distance or more larger distance between valid codes, as you have higher capability to detect the number of errors and also to correct errors. Okay. Now I was talking about distance. Distance in what sense? So one may ask, for example, in binary system, distance in what sense? For example, if I ask you what is the distance between 101 and 001, one way to do that is called Hamming distance. So the Hamming distance is we measure the differences between the bits corresponding bits. For example, the first bit here is 1, the first here is 1, so we have difference, it is 1. The second bit here is 0, the second bit is 0, they are the same, plus 0. The third one is 1, the third one is 1, so plus 0. So the Hamming distance here is equal to 1. Okay, what if we have like 1, 0, 1, the same, but the distance with 1, 1, 0? Okay, the first are the same, so we don't have any error or any distance difference, but here the second are different, so we have 1 plus the third are different plus 1, then Hamming distance here equal to 2. Okay, usually how it is computed, you can compute them by computing the number of ones, that the weight is the number of ones by adding them, because we know that when we add like module 2 summation in digital or in binary system, 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, and 1 plus 1 equal to 0. This is the module 2 summation, and then we compute. This is W is the weight of X plus Y. Then this gives you the number of ones in that summation, and you can see that if they are the same, 0 plus 0 is 0, and 1 plus 1 is 0, and if they are different, then the result will be 1. For example, if you have this code, if I ask you what is the distance between 1, 1, 0, 0, 1, and another code is 0, 1, 0, 1, 1. Okay, what you will do, simply add them together. So 1 plus 0 is 1. Okay, 1 plus 1 is 0. 0 plus 0 is 0. Okay, and 0 plus 1 is 1. And 1 plus 1 is 0. Now count how many ones you have. You have 2. Then Hamming distance equal to 2, because we have 2 ones. 2 ones means that we have 2 differences between those codes. Okay, so this is one way of measuring that distance. It is widely used, especially in block codes. And also we have like another kind, for example, measuring the Euclidean distance, especially that when we don't have we don't threshold the signal like 1 and 0, but we have smooth signal, so the signal is received as it is before threshold, before we make them 1 and 0, then we can have it based on the Euclidean distance. So code rate and redundancy. As we mentioned here, that if we have source data segmented like in the blocks of k bits, so those k bits are called information bits. Okay, and then we have 2 of the power k distinct messages. All of them, they are valid, as the example that I gave with the 3 bits. Okay, the encoder transforms each k bit data block into larger block of n bits. Okay, now this is called code bits or channel symbol. Now we have a new larger number of bits per block. Instead of k, now we have n bits. Okay, n minus k, the difference is the redundant bits or parity bits or check bits. Okay, and the code usually in this case is referred as nk. For example, if you have code with the total number of bits is equal to, let's say, 8, and the number of information bits is 3. So in that case, this code is called 8, 3. Okay, the redundant bits is 8 minus 3 is 5 bits is the redundant bits. The redundancy of this code is n minus k, which is usually we call them q, is the number of redundant bits 5 divided by k. K is 3. So 5 by k is called the redundancy of the code. The term k over n is called code rate. So the code rate here is k. K is the number of information bits here is 3 divided by the total number of bits 8. So the 3 divided by 8 is called the coding rate. For example, in a code with half, it means that each code bit carries half bit of information, because half of the bits in that code will be for information and half will be in parity or check bits, but not necessarily that they are distinct. Sometimes they are mixed together, cannot be distinct directly. Okay, so we mentioned about this coding and throughput. As we said, as we increase the coding bits, it might decrease the throughput, but taking into that in case we use the same modulation technique. But because of coding that we can increase the performance, we can reduce the probability of error, then we can increase the spectrum efficiency, and in that case, of course, we can increase actually the data rate and the throughput by using the coding techniques. We mentioned this before. Okay, block and convolutional code. Let us leave this for the next clip, and next clip will be the last clip in this part. So we will talk about block and convolutional code, and we will see some numerical example about coding. Thank you very much, and see you in the coming clip. Thanks a lot. Bye.